In this problem, we need to solve example 2.3 again, but this time we're going to use the Hamiltonian operator. So the Hamiltonian operator. So first of all, let us remind ourselves what example 2.3 is. So we had this wave function, and then we were given that it looks something like this. So if you graph this out, you have your x-axis and your axis for the initial wave function, and then the curve, the initial wave function looks something like this. It's a quadratic curve. So we're told that the wave function looks something like this. And then in that problem, I'm not going to prove it again. We found that the constant over here through normalization is equal to the square root of 30 divided by e to the power 5. So this is the information that we had in the example. So now we need to find the expected value of the of energy, and then we can apply the formula. So we take the conjugate of the initial wave function times the Hamiltonian operator applied to the wave function itself. So the first question is that why is it that we can use the wave function evaluated at time equal to 0? Don't we have to use something more general? So don't we have to substitute t inside here? So if you break this up, Griffiths actually proved it in his textbook. It actually makes no difference. So if you put a t here or you put a 0 here, the expected value of this energy does not change. So it doesn't matter what you use, and of course it's going to be much easier if we use t equal to 0. So I'm not going to prove why we can use t equal to 0 here. You can look at the examples for that, but for this part we're going to use the initial wave function because it's much easier. So in order to calculate the expected value of energy, we're going to have to evaluate this expression here. So first of all, let us try to figure out what this is. So first of all, what is the Hamiltonian operator? Well, the operator, by definition, is equal to the reduced Planck constant with a negative sign divided by 2m. Then we take the partial derivative with respect to x 2 times. So this would be that one-dimensional case. And then in our case, the initial wave function, as given, is equal to a times x times a minus x. And so if we apply the operator to our initial wave function, so first of all I can pull out the constants first. So I'm not going to write out a, so you know that a is equal to this. So I'm just going to use a for convenience sake. And then we differentiate this 2 times. So this is just ax minus x squared. You differentiate it once, you get a minus 2x. You differentiate it again, you get minus 2. So in the end over here, you get minus 2. And then canceling out, you get a times the reduced Planck constant squared divided by m. So this is one important result. So we found what this component should be. So now we are actually ready to evaluate this integral, because now we can directly substitute what we have already. So the conjugate of the initial wave function, there are no imaginary components, so it's just ax times a minus x. And then we've already found what this should be, and it should be a times the reduced Planck constant squared divided by m, and then dx. And then this goes from 0 to a. So immediately we can pull out the constants first. So we're left with this rather simple integral. So it shouldn't be too hard to evaluate this integral. So we get ax squared divided by 2 minus x to the power 3 divided by 3. And then substituting a inside, you get a to the power 3 divided by 2 minus a to the power 3 minus 3 divided by 3. So this is a to the power 3 divided by 6. So we can substitute this inside directly. A to the power 3 divided by 6. And then this capital A squared, this is just 30 divided by a to the power 5. So this cancels out. So in the end we get 5 times the reduced Planck constant squared divided by ma squared. So this cancels out to a squared. So this is your answer. And then if you compare this with the other method that Griffiths used in example 2.3, you'll see that this is he got the exact same answer. So everything checks, everything is consistent.